Hi, in this video, we're going to take a look at generalized linear models for the purpose of supervised learning. So specifically, we're interested in the predictive analytics aspect. So generalized linear models are a generalization of linear models. I know it's shocking, right? Linear models, generalization. Um, so what we're doing is that regular old multiple linear regression assumes that the residuals are normally distributed, or at least close to it. Well, what about in situations where that's clearly not the case? Maybe a priori, before I build the model, or after I look at the results, I conclude my residuals are not normally distributed with constant variance. Now, there's a couple of different tools that we can do for like transformations, to get get the assumptions that we need. But some situations like counts will never be normally distributed, or 0 1s, things like that. Things for like logistic regression. It just doesn't work out. So what we're going to do, we're going to generalize linear regression to a more flexible format to be able to handle a wider range of data. Now, there's two ways that we would really be using our model. One is for inference, but also another one is for prediction, that we can use generalized linear models for predictive analytics also. One huge advantage that they have on that front is that typically what I see when I'm training my model is what I get when I score my model. That is to say that built models that are built using linear regression, generalized linear regression, tend to perform as well on their like the test set that you have for a holdout as they do for your actual scoring down the line. This isn't the case for other situations where we can have overfitting. And we have tons of diagnostics to help us understand our model better, to help us make sure we don't overfit, to make sure we get the best model possible. And so there's a lot of advantages of using generalized linear models. All right, so we're interested in the situation where it's not appropriate to have a regular old Gaussian distribution for our residuals, and we want to evoke something a little bit more flexible or more tuned to the situation I'm in particular. All right, so there's some advantages of generalized linear models. First of all, they're flexible. They can handle a wide range of response variables. So logistic regression includes 0, 1 variables. That's actually a generalized linear model. And we could also have like Gaussian distribution. We could have Poisson distribution, which are strictly counts. And we can also do regular old linear regression. And we could do combinations of different distributions possibly with the Tweety distribution. Now, the interpretation is compared to more complicated models, really as good as it gets. So this is probably the most flexible model structure that you can get and still be able to make an inference on what's going on. Now, we're going to talk about link functions in a moment, in that we're going to have to include our link function in our interpretation, so it can get kind of hard to figure out what's actually happening. But I can usually at least figure out like coefficients. If this variable goes up, my target variable goes up or down relatively. And there's a wide application to generalized linear models. And so these are really, to me, advantageous for a wide range of situations. All right, so, of course, everything I do on my YouTube channel involves code. I show you how to do it. I show you complete code. I don't omit anything. And I'm going to prepare my workspace. So I don't want to print out too many digits, so I just print out 2. I want to avoid scientific notation, so I crank up the SciPen parameter, and warning -1 is if there's any warnings, I just don't want to bother with it. Now I'm removing any artifacts from my workspace so that I don't have any problems going on. And then I'm going to be using piping from the tidyverse. And so I can invoke just the magrittr package to get piping going. Now I'm going to be doing a regression data set and a 2-level categorical logistic regression model also. This one is regression data. Here's the house prices data set that I prepared in another session. And to make things a little bit easier to run through, I am going to put all of my predictor variables that I'm considering using into a vector. I find that this is a good practice. Typically on real life projects, I'll have a vector of like my ID variables are in a vector, the names of them. And then I'll have for like my partition variables will be in another one. Target variables, categorical predictors, numeric predictors, and so on. And I find that this is best practice for having like good modeling. Now, the house prices data set is coming from Kaggle. It's from a Kaggle competition, and the test set that's coming from Kaggle doesn't have any target variable values. Well, that doesn't really help me for the purpose of fitting a model in teaching on a lecture. And so I'm taking the point of view that I only want the data that I have my target variable for. So here I am filtering out all of the data that I don't have a target variable for, and then I'm splitting my data 50-50 into train and test. Now, when we work with generalized linear models, there's three components. There is a random component, there is the linear combination, and then there's the link function that is my crosswalk between the two. All right, so the linear combination, that is the right-hand side of this equation here. Now, that is what we're really familiar with from multiple linear regression. What we're going to do, how we're going to change this up, is that the left-hand side is going to be like an average. So the target variable on the left-hand side is not the actual target variable for our data. From a model point of view, it involves the average, and that's what's important. So over here, I'm going to have the link function of the conditional average is what I'm trying to put on there. And so because I'm trying to model the average, you'll notice I don't have an epsilon on the right-hand side because I'm not trying to model the actual value. I'm trying to model the average, conditional average of, given that the right-hand side is correct, that we know all these values, what will be the link function of the average? Okay, so the random component, specifies what's the distribution for my response variable. And so all the GLMs have different ones, different distributions, and they're going to be using some form of exponential family. All right, so if you've taken mathematical statistics, you've taken stat theory, you know what an exponential distribution is. It's basically just a class of distributions, probability distributions that are highly useful, have a lot of nice theoretical properties. Because of those theoretical properties, we're able to build up this generalized linear model approach. All right, so the first one I want to talk about is the Gaussian distribution. And so here, this is actually just regular old multiple linear regression that we're familiar with. Now, the next most common one is going to be logistic regression. There, we're going to be using the binomial distribution. Now, if you think for a moment, if I've got 0, 1's target, so what we're doing, I'm taking a 2-level categorical target variable, and I connect them over as 0s and 1s in my coding. And then I'm going to be doing logistic regression. Now, you go, well, hey, wait, 0s, 1s, isn't that Bernoulli, not binomial? That's correct. But what's happening is that when we specify the predictor variable values, if I have multiple observations for the particular x values, and when I say x values, I mean all the x's here, exactly the same, multiple observations for the same levels of all of the target of all of the independent variables, then I'm going to have a mixture of what's going on for my target variable. Sometimes there'll be 0s, sometimes there'll be 1s. And so there, because of the 0s and 1s aspect, there's multiple observations. It's no longer Bernoulli, it's binomial because of multiple observations for one particular value. Now, frequently with our data, we don't actually have true binomial. We could actually have just used Bernoulli, but it doesn't change anything for us. We'll run it exactly the same. So binomial is a little bit more flexible. Now, Poisson, this is when we typically use this for count values. Specifically, if I'm dealing in a situation where we start at 0, then we go to 1, then we go to 2, then we go to 3. So something like sequentially things happening. So like the number of lightning strikes over a week in a location. For there, you start with 0 strikes, then there's 1 strike, 2 strike, 3 strike, and so on. And that's when we use Poisson distribution. Now, the gamma here, this is a continuous distribution, and so it's non-negative and it's skewed right. And so if I see that that's what I've got going on with my data set, that and it looks like Gaussian distribution is not appropriate, I can go over to gamma. Now, inverse Gaussian, also called the wall distribution, these are two different distributions, but we can go non-negative and it's also skewed right. Quasi-binomial is more flexible than the binomial family. Specifically, it handles, instead of actual counts or zeros and ones, it'll handle fractions of values between 0 and 1. Quasi-Poisson, we'll use that for over dispersed Poisson distribution. And then the Tweety, this is a very flexible distribution, but that flexibility comes at a cost. So here we could have Gaussian, we have Poisson, we could have a gamma distribution. We could have something in between Poisson and gamma. So like if I have a zero inflated target variable or inverse Gaussian, all of these are possible with the Tweety distribution. The catch with this is that I have to go through the process and identify what's the distribution parameter for the Tweety distribution. This can take a long time. I've seen this used a few times in insurance. This is very flexible and it'll work, but I've seen data scientists have to really fight to be able to get the best parameters for this and have issues with convergence. Now, the next component of a generalized linear model is that linear combination. And so here I'm rewriting this equation, but I want to emphasize the right-hand side. So this right-hand side is a linear combination of our coefficients and our predictor variables. And that's, that's just the right-hand side over here. And here this is our intercepts. Each of the other betas are coefficients, and each of the x's are predictor variables. Now, the link function provides a crosswalk for us. And so I've got g of the expected value. And so the link function is how we connect that expected value to that linear combination on the right-hand side. Our link function is going to be an invertible function. And this, gives us that way of going back and forth. Now, something that's important to understand is that because I'm modeling the expected value, I don't need that epsilon in there like I did when I did multiple linear regression. All right, so let's talk about different link functions. All right, so if I have the Gaussian family, I have the identity, which is multiple linear regression. I have log and I have inverse as my link functions. And so how I'm going to invoke this. So when I do generalized linear model and base R, it's just GLM, generalized linear model. I specify the formula. I specify my data. Notice that in my data, I'm only restricting things down to the training data set. And here I'm restricting it down to just the parts I want in the formula. So here I've got my predictor variables and I've got my target variable. Now to specify Gaussian, I've got two different ways I can do this. I can either put Gaussian as a word, a string in quotations, or I can take Gaussian as a function. And so here I'm taking the Gaussian function. Now, and then I'm specifying which link I want. So here, this part specifies the family overall. This specifies this specifies the random component. This specifies the link to connect my linear combination to the random component. All right, and so I've got this. Now, each of the different families parameters has a default link function. If you're okay with the default link, I don't have to put in anything inside the function. It's perfectly fine to go without. And so if I was just to leave the Gaussian as is without a link function, it would do standard multiple linear regression. In fact, GLM, if I didn't specify the family, it would automatically go to Gaussian as the default parameter. And so we can see our results. Now here, I'm going through Gaussian again, but now I'm using the log of the expected value for my modeling. And if I look through, I'll get different coefficients for this. Now, what I did when I built these models is I actually built the models with all potential predictor variables, did backwards elimination, and then reduced down the formula to the backwards elimination output. And so these are all at least going to be semi-decent models that I'm building here. And then next, for Gaussian, I can have an inverse for my link function. We can go through and just check out the coefficients. So we have so what we're doing on the left-hand side, I have that function of the expected values while modeling, and the right-hand side is the betas and the x's. Now for gamma, our link functions are the identity, log, and inverse, the same ones that we had for Gaussian. And so here, we're gamma is going to be assuming that there is like a skewed right distribution going on when we're doing the fitting. And we'll go through, do exactly the same thing we did before. Now, for the purpose of making predictions, if I'm doing predictive analytics, I honestly don't care what the model structure is. I just want the best model I can get. And so I'll be using my train test split, or actually I'll be using my train and validation set to select the best possible model and going forward. So that's the way that we will, for predictive analytics, we would prefer to move forward. If I was in a situation where I wanted things, let's say I'm in a small data situation or maybe an inference situation, I'll use other things like AIC and other diagnostics that come out from the function to decide on what is the best model. So here's gamma with the log link. And here's gamma with the inverse link. Now, inverse Gaussian, we have the choice of the identity, log, and inverse, just like with gamma and Gaussian, but I also have 1 over mu squared. All right, and so inverse Gaussian is inverse dot Gaussian as a function, and then I put in, the link that I want. Now, some of these can be difficult to get to converge. If you have trouble getting a model to converge compared to other ones, the ones that have trouble converging usually are not the best models anyway. So if it's running a real long time, it's okay to kill it and just bounce to another model structure. Inverse Gaussian with the inverse link function. And then now we get down to 1 over mu squared as my link function for inverse Gaussian. Now, the Tweety distribution is very, very flexible, and we can do a whole range of different distributions, and all of them are coming from an exponential family. So if I put 0 as the parameter, I'm going to have normally distributed. If I put 1 for Poisson, what I'll get. If I put 2, I get gamma. If I get 3, I get inverse Gaussian. And anything greater than 2 is considered stable when I'm making sure that we have support on the positive real values. Now, I want you to think about something. Here's Poisson, here's gamma. Poisson is a discrete distribution. What's going to happen is if I do a parameter between 1 and 2, I'm actually going to end up getting a compound Poisson distribution with a non-negative mass at 0. All right, well, why would that be important? Why would that be useful? Well, think about something like maybe insurance claims that when we're talking about dollar amounts. So a client for an insurance company, month after month, most of the time they're not making a claim. So they've got a claim dollar amount of 0. But when there is an accident, there's going to be a distribution for the amount that's going to be paid. And so it could be, a situation where it's like thousands and thousands of dollars, it's a distribution, or it's 0. And, we want to be able to handle that. So that's going to be called, like a 0 inflated model. So if I handle something between 0 and 2, I'm going to have a mixture of the count distribution, which can account for zero inflation, and the gamma distribution. And so this gives me a way of using a very nice model structure for that weird situation where it's zero or a lot of money. Now, a disadvantage of Tweety is that we have to find what the parameter value is, and we have to, get the model to converge and have it compute, and that can take a while. But if I have an idea of what distribution I want, I can at least set up a starting parameter that puts it in the ballpark of where it's going to, it's ultimately going to land, and that will speed things up. Now, the Tweety distribution is not in base R, and so to run this, I have to use the StatMod package. There are other packages. I choose StatMod because on my internet research, that looked like it was a pretty common one to use. My last peer review for work was actually a Tweety distribution, by the way. And, so we can just see what's going on here. Yeah, so if I put in 0, this will be Gaussian. If I put in 1, that's Poisson. Here, this is a combination of Poisson and gamma. So this will have a zero inflated model. Here, this is going to be gamma. And then I believe that's inverse Gaussian. All right, so the next one I want to talk about is Poisson distribution. Now, one option that I could do is I could fit a Tweety distribution, specify a Poisson distribution, and then handle counts that way. It'll be more efficient and it'll be better and it'll be faster if I just specify its Poisson distribution and not worry about this Tweety business. All right, so here we're making the assumption that our target variable are counts. And something that's, if you look at Poisson distribution, how it's actually built up, from a point of view of like math theory, that Poisson distribution starts with 0, then 1, then 2, then 3. So if we're talking about, let's say, number of broken light bulbs on a factory floor, and so they're coming, a factory that builds light bulbs. Well, there's when they start, they start the week, start the day, start the month, whatever you're measuring over. When they start the time span, they're at 0 failures, and then there's a bad bulb comes out, then another bad bulb comes out, then another bad. So when we're talking about Poisson distribution, we are interested in a situation where we start at 0, then we go to 1, we go to 2, we go to 3, we go to 4, and so on. If it's other situations, like let's say we're doing counting on dice, I count the number of dots on die as I roll while I'm playing a board game or Dungeons and Dragons or something like that, then that's not Poisson distribution, because it's like that 5 is just generated all at once. And so Poisson probably would be the best generalized linear model to fit for that, but we would want to know that it's not the best fit possible, at least hypothetically, theoretically, not the best. Oh, in Poisson, we have log, identity, and square root. So square roots make an appearance for the first time in this video. So Poisson, I believe the default is log. I'm not 100% sure of that, but it's, we can look at that later. We also have square root, and we have identity. Now for binomial, and this is by far the most common generalized linear model when people actually call GLM, is binomial family. So that's logistic regression. All right, we've got logit, we got probit, quotient, log, and C log log. Okay, so in general, most of the time, we want to use logit. Logit is very flexible, and it can handle most cases pretty well. So if logit is not the best choice, but I went with logit anyway because I made a mistake, usually it's not that bad. If it, choosing logit when it's not the optimal isn't much of a loss, but choosing another one when it's not optimal can be rather detrimental to your modeling. All right, so here I'm loading my data, and here we're using the edible or poisonous mushrooms data set from Kaggle. And here, once again, I fit before the video, I fitted a model, I did backwards elimination, and when you see the formula for each of these, the backwards elimination, it concluded that this was the model to go with. Here we're using logit for it. Here we're using probit. Probit invokes the Gaussian distribution, and I found, in my experience, the economists like probit a lot for that theoretical interpretation. I feel like logit is the better way to go. Do whatever your stakeholders want you to do. Logit has an interpretation that connects to log odds, but probit connects to Gaussian distribution. Whatever your audience wants, whatever your stakeholders wants, that's what you should go. If you're strictly interested in predictive analytics, go with the one that gives you the best predictions. Now, next one is we're using the Quasi distribution. Now, this next one, log for binomial, I couldn't get it to run. At least on my machine, on this data set, I couldn't figure it out. So I'm showing the code, but I could not get it to go. And then the next one is C log log. This is frequently used in survival analysis. Now you'll notice that it took quite a few iterations to get this to converge. All right, so when it takes a lot of iterations for it to converge, frequently that's a sign that I'm not going to have the best possible model, that other options would be a better choice. And so here we have an AIC of 74. Here we have 74. Oh, so it's tighter than I thought. So all these are pretty tight. I would personally pick logit. Now the quasi families are more flexible than their corresponding namesakes. And so basically we just want to use these when the regular versions of the distributions are not as flexible as we need, or they're not performing as well as we want them to. And I've professionally used the quasi binomial distribution quite a few times. It's worked very well when I needed, just to be able to handle a wider range of data. Like instead of having zeros and ones, I had fractions to model on. All right, so quasi, for the family, and the link is identity. We also have quasi with the inverse link function, quasi with log. And so far, we've only been doing regression problems. So here we have a link of 1 over mu squared. And here we have the square root. All right. Now, on the next ones, I'm going to show you that they'll run with target variables between 0 and 1, but they won't work if you have a regular old regression problem. So if I have values outside of 0 and 1, let's say I've got like a negative value or greater than 1 in my target variable, the ones that I'm going to show you in a moment won't work. So quasi with a link of logit. Here's probit, invoking some Gaussian residuals. You'll notice that when I get into the more exotic features or exotic types of modeling, features start dropping off. The things are not as well established, and people have not taken the time to build up the tools to support us in our modeling. Here is, that survival analysis C log log. All right, so now there's something called over-dispersion in Poisson regression. Over-dispersion is when my variance significantly is greater than my expected value. If you remember the Poisson distribution, the lambda parameter is both the expected value and the variance. So if we see greater variance than our expected value, then we typically want a different modeling structure than Poisson. All right, so what we'll do when I'm looking at my data, I will compare the sample average to the sample variance. If there's a big difference, that's a sign I don't want to be using Poisson distribution. All right, so why do we want to worry about over dispersion? First and foremost, we'll get like air, we're going to end up by having a stronger model structure than we should have. We're going to be underestimating some things. So if I'm using Poisson regression when it's not appropriate because of over dispersion, Poisson regression will make things look better than it really is. And I don't like that situation. I want the situation where I know what's going to happen when I launch my model. Also, the model fit won't be as good. I just won't get as good of predictions as I would with a more precise model structure. Now, what are the causes of over dispersion? First and foremost, misspecification of the model. And so, like, wrong model structure, wrong formula structure. Maybe I'm missing predictor variables, or I have predictor variables in there I shouldn't have. Like I have, covariance going on between predictor variables. Now, excess of zeros. And so if I have a whole bunch of zeros in there, Poisson distribution is going to have there's going to be like two signals going on, and Poisson distribution won't be a good fit. I would want to bounce to that Tweety distribution potentially. And we can also have problems with heterogeneity. And so there might be a presence of some other variable that's going on that isn't accounted for in my data set. And then we can also have like subpopulations of my data that have different features and different relationships between the variables that's not present in my data set for me to be able to detect. So how do we handle over dispersion? First and foremost, we can switch to the negative binomial regression. And I have another video on YouTube for that. I'm not going to go any deeper to this because really our point of view, if I'm doing predictive analytics, is I try a bunch of different families, I try different lengths, I just try a whole bunch of different models, I get the best model I can, I run with it. We usually don't worry about the theoretical aspect as much in predictive analytics. So something I can do is, basically go and get better data, get data that I'm missing. And we can also, put in like starting values for our parameters that if I a priori know what the values should be, I can put them in for my starting values and help improve model performance that way. And then I can also switch over to zero inflated models, such as that Poisson gamma balance modeling situation. All right, so got some homework for you. Hopefully this is quick and easy. I hope that this doesn't kill your weekend, but that's all I've got for you. Life is short. Do math.